Welcome to iLecture Online, and here's a good example of how to apply the concepts of electrical potential and electrical potential energy to a problem like this. Let's take a look. It says here that we have two protons that are 2 times 10 to the minus 10 meters apart. That doesn't seem like a lot, but for protons that's quite a distance. And they're pushed together slowly until they're 3 times 10 to the minus 15 meters apart, and that's pretty close. That's about the size of an atomic nucleus. How much work is required? And then, if they're let go, how fast will they be moving when they return to their original position? All right, how do we start a problem like that? Well, if you're really confused at this point, like I am, well, you draw a diagram. So you can take a picture here. Let's see here. We have a proton, and let's say that at the start, they're apart from one another a distance of 2 times 10 to the minus 10 meters. And now we want to bring them together until they are much closer, like so. And let's say now the distance between them is 2, no, it doesn't say 2, it says 3 times 10 to the minus 15 meters. Very close together. It says how much work is required to do that. All right, work, potential energy. Also, electrical potential. Let's write some equations down to kind of get a feel for this. If we assume for a moment that this one is stationary and we bring this one closer to a position like so, we have now moved it a lot closer from where it was before. The potential at this location due to the charge over here can be expressed as V is equal to KQ over R. And let's assume that this here is Q, or call it Q1. Let's call this Q2. And R would then be the distance from there to there, so let's call this R. We now have an equation that tells us the potential at that location. If we now move another charge there, like Q2, we then know what the potential energy is. The potential energy is therefore equal to the potential at that location times Q2, which in this case, the potential energy, or the potential is equal to this, so it's equal to K Q1 over R times Q2. So that's the current potential energy the system has when those two charges are that far apart. And then we can say, well, what would be the potential energy when the charges are much closer, like they are here? And then when we take the difference, that would be the work done to get the two protons to be that close together. All right, so let's call this potential energy at position 1, call this position 1, and let's call this position 2. We'll figure out the potential energy of position 2. And let's call this R1, and let's call this R2. There we go. Now let's plug in some numbers, and I did bring my calculator, so this is equal to 9 times 10 to the 9th newtons meters squared per coulomb squared. Multiply that times Q1, which, it's a proton, so that would be 1.6 times 10 to the minus 19 coulombs. And the other charge is also a proton, 1.6 times 10 to the minus 19 coulombs. And take the whole thing and divide it by the distance between them, and that would be 2 times 10 to the minus 10 meters. So that would be the potential energy in joules. So let's see what that is equal to. It's 9 e to the 9th times 1.6 e to the 19 minus. We have to square that. And then we divide that by 2 e to the 10 minus equals. And I get something, it says 1.15 times 10 to the minus 18 joules. Okay, so that's the energy of the system before I start bringing the two protons together. Now, what will be the energy or the potential energy of the system when the two protons are this close together? That would be PE2, potential energy 2, is equal to V. Let's call this V1 and V2. V2 times Q2, and V2 would be the potential when you're this close to the charge, so it would be K times Q1 over R2 times Q2. And so we get the exact same equation, but now the distance is much closer. So we get 9 times 10 to the 9th newtons meters squared per coulomb squared times 1.6 times 10 to the minus 19 coulombs times 1.6 times 10 to the minus 19 coulombs. Those are the two charges. And we divide the whole thing by now the new distance, which is now 3 times 10 to the minus 15 meters. All right, so let's calculate that. So multiply that times 2e to the 10 minus, divide by 3e to the 15 minus equals, and now we have a potential energy of 7.68 times 10 to the minus 14 joules. All right, so how much work did we have to do to bring the two together? Well, the work then would be equal to the potential energy 2 minus potential energy 1. It would be the difference between the two potential energies, so which is equal to 7.68 times 10 to the minus 14 joules minus 1.15 times 10 to the minus 18 joules. And considering the significant figures here, that would be equal to 7.68 times 10 to the minus 14 joules. This doesn't even make any dent in the energy that it will have when they're that close together. All right, so that's the amount of work done. That's the first question, to get the two protons that closely together. Now, the second question, they say, well, how fast will they be moving when we let go and they start speeding away from one another, because there's a lot of forces pushing these two protons apart, when they get back to the original position. So when this one speeds out, so it goes back to this position, and well, it doesn't stop there. It will continue going at very high velocity, but how fast will they be when they reach their original position? So V final equals question mark for the second part of the question. All right, there I think we have a conservation of energy situation. We will convert the initial potential energy they have when they're pushed together like this to the final kinetic energy they have when they're that far apart. So we can say energy initial equals energy final. And so initially we have the potential energy initial, and at this distance the potential energy is so small we can just ignore it. So the potential energy initial will be equal to the kinetic energy final. And the potential energy initial, we have that is equal to 7.68 times 10 to the minus 14 joules. And the kinetic energy final will be 2, because there's two protons, 2 times 1/2 times the mass times the velocity squared. The assumption is that there's total symmetry in the problem here, and that both of them will be moving with the same kinetic energy and the same velocity when they reach these respective positions. Now you can see that the 2 cancels out to 1/2. If we solve this equation for V squared, we have V squared is equal to the original potential energy of 7.68 times 10 to the minus 14 joules, and divide the whole thing by the mass. Then of course to find the velocity we have to take the square root of that. So the velocity will be equal to the square root of 7.68 times 10 to the minus 14 joules divided by the mass of these protons. If I remember right, the mass of a proton is 1.67 times 10 to the minus 27 kilograms. All right, let's now plug that into our calculator. So divide that by 1.67 exponent 27 minus equals, and then take the square root of that, and that is rather fast. That's 6.8 times 10 to the 6th meters per second. Let me verify that. 6, yeah, that's right. Wow, 6.8 million meters per second, or 6,800 kilometers per second. Wow, that's quite a distance. They would be moving so fast I could travel across the country and beyond in 1 second. And that's the answer for the second part of the problem. So, recapping real quick, we were told that we were going to take two protons at a certain distance and push them slowly together until they're very close together. How much work did that take? And secondly, when we let them go, how fast are they moving when they get back to the original position? So the approach is to say, all right, what is the potential at this location, even if this charge wasn't there, due to the presence of this charge, which is equal to V, which is K times Q1 over, we'll call it R1. Then when we place a charge there, we now know the potential energy of that system. So we take the potential V, and we'll multiply times the charge we place there. Now we're given the value of the potential energy of having the two protons situated like that, and then we calculated that it was equal to 1.15 times 10 to the minus 18 joules. The second thing we do now is we then imagine, if we bring them this close together, what's the potential at this location, this far apart from that charge. And again, that would be V2, and V2 of course now would be Q1 times divided by R2, R2 being a much smaller distance. And then we multiply times the charge when we place it over here, and now we have the potential energy of the system when they're very close together, and of course a much bigger number. The difference between the two is the work that's required to bring them this close together, so we simply subtract the two potential energies. Then for the second part of the problem, if we let them go and they fly out both directions, how fast are they moving when they're situated there? Then, well, what we can say then is that the original energy they had by being this close together, the potential energy initial, which we calculate over there, will now be converted to kinetic energy when they're over here. We can probably ignore how much potential energy they will have when they get there, because that's a very small amount compared to their original potential energy. In the kinetic energy, if you remember right, that's 1/2 mv squared. Since there's two protons, we multiply times 2. The 2 cancels out to 1/2, and then a little bit of math. We can then find the velocity of the protons when they reach their original position. And that's how you do a problem like that. Okay, hopefully this helps you see how understanding electrical potential energy and electrical potential can help you solve these kinds of problems. Right? I have a few more examples for you if you want to stay tuned for the next video.